Hey everybody, today I'm here to talk to you about how encryption works. If you already know all this stuff and just came here to learn about decryption with ExtraHop, feel free to skip ahead by clicking the link in the upper right hand corner right now. But for everyone else, let's get started. First up, we have classic Rsa Key Exchange. This is sort of the old way of doing things, also known as the less safe way of doing things, also known as the not recommended way of doing things, and you'll see why in a second. Just some quick terminology before we get into it. We have two kinds of keys we're going to talk about today. We have asymmetric keys and symmetric keys. Asymmetric keys include public keys, which function basically as locks. They encrypt data so attackers can't see what's inside, and private keys, which are basically the corresponding keys to those locks. They decrypt the stuff that's been encrypted with the public keys. Symmetric keys only have one kind of key, and that's called a session key. A session key is basically a lock and key pair. If you encrypt data with a session key, then you can also decrypt it with that same session key. Here's how classic key exchange works. A client talks to a server, and the server takes its certificate, which includes its public key, and sends that certificate to the client. The client then derives some value, we're going to call it X, and the client encrypts X with that public key it got from the server. Then it sends that encrypted X back to the server, and the server can then use its private key to decrypt it. So now the client and the server both have X, right? So from X, both the client and the server are able to derive identical symmetrical session keys. Now the client can use that session key to take sensitive information and encrypt it, send it over the wire to the server, where the server can apply the same session key that it derived and decrypt it. But what happens if an attacker gets in the middle here? Well, things are initially fine. Although the attacker can listen in when the client sends X to the server, that value is encrypted. And if the attacker sees the sensitive data that the client sent to the server, that's encrypted too. But what about in the future? It's possible that the attacker can gain access to the server's private key. Maybe the attacker compromised the server, maybe a court ordered that the private key be made public. That's happened in the past before. Another possibility is that a new vulnerability is discovered, like Heartbleed, which discloses the private key. But whatever the circumstances, if this happens, the attacker can then decrypt X. And if they decrypt X, then they are able to derive that session key and decrypt the sensitive information. But that's not even the worst part. The real issue here is that that private key wasn't just used in one transaction. That private key was involved in any number of transactions that could have occurred over months or even years. So if the attacker was listening into all of those conversations and they gain access to that private key, they can use that private key to decrypt that secret value X for all of those transactions, and from that X they can derive the session keys and decrypt all of the information that they've been listening into. Which is why that method is being phased out. You want to be using perfect forward secrecy, also known as the safe way to do this, also known as the recommended way of doing this. This is what TLS 1.3 uses. TLS 1.2 can also do perfect forward secrecy, but it's got to be using the right cipher suite. In order to generate the keys needed for data encryption, PFS relies on some very complex math. Now, I'm not going to get into the math here. There's a lot of complicated equations and algorithms that I don't understand. So in the diagram, I'm just going to draw a box. And that's what's going to represent all the math being done. There are really only two things that you need to know about the math. The first is that if you take a value, let's say A, and you put A into the math, you can't extract it out of the math. The math makes it impossible for you to figure out what the original value was. The other thing you need to know about the math is that it doesn't matter what order something goes into the math. So let's say I take the math and I go put A into the math, and then I put another value B into the math. And then let's say you also have some math, but you first put B into the math, and then take A and put that into the math. The result of those two mathematical functions are the same. They are interchangeable at that point. So here's how PFS works. First, the client tells the server what kind of math it knows, and the server agrees to use one of those kinds of math. Then the client generates a secret value, we're going to call it A, and it takes A and it puts it into the math, and then sends the product of that math to the server. And then the server similarly generates a secret value, we're going to call it B, and puts B into the math, and then it sends that product to the client. Now both the client and the server have their own secret values and some math that contains each other's secret values. So the client adds A to the server's math, and the server adds B to the client's math. And from before, we now know that the results of those mathematical functions are identical, and so from those results, the client and server can both generate identical symmetrical session keys. And with those keys, they can encrypt important information on one end and send that encrypted data over to the other machine, where the other machine can decrypt that information with the same session key. So what if an attacker gets in the middle here? Well, the attacker is able to see math A on the wire, and they're also able to see math B on the wire. But here's the thing, math A and math B together do not equal math AB. The reason is that the attacker can't extract A out of math A to put it into math B, and similarly it can't extract B out of math B to put it into math A. They could in theory add the entire result of math B and put it into math A, but that is not the same as math AB. What about in the future, though? That's where we ran into trouble with classic key exchange. Well, after the transaction is done, the client goes away, and when that happens, the server gets rid of the session key. Which means even if the attacker at some point in the future gains control of the server, they still can't get the session key. The server is like, I'm sorry man, I threw that thing away. However, no key is completely uncrackable, right? If an attacker is really committed, they can take math A and math B and add a lot of time and a lot of compute power, and eventually they might be able to derive math AB. And with math AB, they can derive the session key and decrypt the important information. But here's the cool part. Because math AB was only used to encrypt that one transaction, it can only be used to decrypt that one transaction. Unlike with classic key exchange, if the attacker tries to apply math AB to those other transactions, it won't work, because those transactions all had their own distinct math values. And because it takes a long time and compute power to crack just one of those session keys, it's generally not worth it for attackers to try that. And that's where the forward and perfect forward secrecy comes from. Even if an attacker is able to compromise the server at some point in the future, there's no one private key that they can obtain to unlock all past transactions. Now that we have a basic understanding of encryption, we can move on to learn how decrypting traffic can help keep your network more secure. Thanks for watching.